Welcome to the General Chemistry 2 class. This section is on chemical thermodynamics. This lesson is about second law of thermodynamics. And now, let's begin. In this lesson, we will explain the second law of thermodynamics and its significance. Let us recall from previous lesson that the first law of thermodynamics states that in an isolated system, energy is neither created nor destroyed, hence conserved. Mathematically, it can be expressed as eternal energy equals heat plus work. The second law of thermodynamics states that in an isolated system, the entropy of the universe for a spontaneous change process or reaction is increasing. That is, entropy change of the universe is greater than zero. This law is consistent with the natural tendency for reactions to proceed with maximum entropy or from an ordered state to disordered state. A reversible reaction is a reaction in which the reactants are converted to products while the products are converted back to reactants. The entropy change of the universe for a reversible reaction is zero. For the following reaction, the entropy change of the system at 25 degrees Celsius and 1 atmosphere, which is also called the standard entropy of reaction, can be calculated as follows. Standard entropy change of the reaction equals sum of standard entropies of products minus sum of standard entropies of products. A related law to the second law of thermodynamics is the third law of thermodynamics, which states that the entropy of a highly crystalline substance at the absolute zero, 0 Kelvin or negative 273.15 degrees Celsius is zero. Entropy increases as the temperature increases, with a significant difference in magnitude as the substance undergoes phase changes, for example, melting, evaporation. The third law of thermodynamics enables us to determine the absolute entropy of substances at a given temperature, unlike internal energy or symbolized as U, and enthalpy symbolized as H, in which the absolute values are not directly measurable. The entropy change of a substance at 25 degrees Celsius is value that is in reference with the entropy at 0 Kelvin, which is equal to 0. Thus, the entropy change at 25 degrees Celsius is also equal to the absolute entropy at the same temperature. Example number 1. Calculate the standard entropy change accompanying the following reaction. Solution. The standard entropy of the reaction is twice the standard entropy of hydrogen fluoride less the sum of standard entropies of hydrogen and fluorine. Substituting the given values, we obtain standard entropy of reaction 14.087 joules per Kelvin mole. In accordance with the first law of thermodynamics, the heat absorbed by the system is released by the surroundings. Likewise, the heat released by the system is absorbed by the surroundings. The entropy change is related to the amount of heat transferred at constant temperature according to the equation entropy change equals heat transfer divided by the temperature in Kelvin. The derivation of this equation is beyond the scope of this lesson. At constant pressure, the entropy change of the surroundings is equal to enthalpy change of the surroundings divided by the temperature in Kelvin. It is also equal to the negative enthalpy of reaction divided by the temperature in Kelvin. Example number 2. The following reaction has standard enthalpy of reaction equal to negative 546.60 kilojoules per mole. Calculate the standard entropy change of surroundings. Solution. Standard entropy change of surroundings equals negative enthalpy of reaction divided by the temperature. Substituting the given standard enthalpy of reaction and the temperature, which must be in Kelvin, we get standard entropy change of surroundings equals 1833.3 joules per Kelvin mole. Recall that the entropy change of the universe is the sum of entropies of the system and the surroundings. Example number 3. Considering the calculated delta S naught of the system and delta S naught of the surroundings for the reaction hydrogen plus fluorine forming hydrogen fluoride, determine whether the reaction is spontaneous or non-spontaneous. Solution. We can determine the spontaneity of the reaction from the standard entropy change of the universe. This value is the sum of the standard entropy change values of the system and the surroundings. Again, the standard entropy change of the system is the same as the standard entropy change of the reaction. Substituting the values obtained from examples 1 and 2, we obtain standard entropy change of the universe, which is equal to 1847.3 joule per Kelvin mole. Since this answer is greater than 0, the reaction is spontaneous. In a previous lesson, we learned that melting of solids above the melting point and freezing of liquids below the freezing point are spontaneous reactions. The second law of thermodynamics can explain why these phase changes are spontaneous. Melting. Melting is the process in which a solid turns into liquid. Molecules change from a less disordered state to a more disordered state, so entropy change of the system is greater than 0. Melting is endothermic, so enthalpy of fusion is greater than 0. As a result, entropy change of the surrounding is negative. At the melting point, entropy change of the system equals negative entropy change of the surroundings. Thus, entropy change of the universe equals 0. At this temperature, the process is reversible. Solid and liquid phases of the substance coexist. Above the melting point, entropy change of the surroundings is less negative, making entropy change of the universe greater than 0. Thus, melting is spontaneous above the melting point. Below the melting point, entropy change of the surroundings is more negative, making entropy change of the universe less than 0. Thus, melting is non-spontaneous above the melting point. Freezing is the process in which a liquid solidifies. Molecules are both from a less ordered state to a more ordered state, so the entropy of the system decreases in the process. Since freezing is an exothermic process, or enthalpy of freezing is less than 0, the entropy change of the surroundings is greater than 0. At the freezing point, the entropy change of the surroundings equals negative entropy change of the system. Thus, the entropy change of the universe equals 0. At this temperature, the process is reversible. Liquid and solid phases coexist. Below the freezing point, entropy change of the surroundings is more positive. As a result, the entropy change of the universe is greater than 0. Thus, freezing is spontaneous below the freezing point. Above the freezing point, entropy change of the surroundings is less positive. As a result, the entropy change of the universe is less than 0. Thus, freezing is non-spontaneous above the freezing point. Here is the summary of the spontaneity of melting and freezing. How we analyze melting applies to the other endothermic phase changes, evaporation and sublimation. Likewise, our analysis in freezing is applicable to exothermic phase changes, condensation and deposition. To summarize, the second law of thermodynamics states that in closed system, the total entropy of spontaneous reaction is increasing. The third law of thermodynamics, which is related to the second law of thermodynamics, states that the entropy of a highly crystalline substance at the absolute 0 is 0. So here are the references. And that would be all. Thank you. Welcome to the General Chemistry 2 class. This section is about the second law of thermodynamics. And now, let's begin. Question number 1. Match each law of thermodynamics in column A with the correct description in column B. Number 2. What is the standard entropy change of reaction? Select the correct answer. Number 3. What is the entropy change of the surroundings? Select the correct answer. Number 4. What is the entropy change of the universe? Select the correct answer. Number 5. Determine the reaction's spontaneity. Select the correct answer. What is the entropy change of reaction? Select the correct answer. Number 7. What is the entropy change of the surroundings? Select the correct answer. Number 8. What is the entropy change of the universe? Select the correct answer. Number 9. Determine the reaction's spontaneity. Select the correct answer. And number 10. Match each phase change in column A with the temperature in column B at which the process is spontaneous. That's all. Thank you.